All right, we are recording. Next, we can. How many? 7 participants. We can maybe wait 1 minute. Today I will do chapter 6. We can see on the lecture plan. I have it here. Yeah. So we will do chapter 6 today. Not completely chapter 6. Send the link again. All right, we will send the link again. Let's do that. Let's do that. How can we do that? Invite. And did you get all get access to the cameras again? Because the people told me that they will fix it, and they said they already fixed it. But I don't know. I didn't check with you. Oh, great. Great. Okay, so yeah, it looks like people, we will be 7 participants. I don't know why is that. Usually we are like 20 or so. Maybe someone wants to look on YouTube. Anyway, yeah, so we will take chapter 6 today, or almost everything from chapter 6. Then we will do the last parts of chapter 6 on Thursday, and also do chapter 4 on Thursday. And after this, we are finished with the book, and we will do some some material from different sources, and at least for the code/Kademlia and Bitcoin parts, I will share some papers for you to read beforehand, and we'll the plan is to kind of yeah, go through the protocols, present the protocols, and maybe also you can use this as a way for to get some tips of what you need to look for in your own paper or project. And one more thing, that this project introduction, I will we will probably introduce this in the next coming weeks, but so I will share the project to you, but you're not allowed to start working on this project before you finish the labs. So I cannot give you the full exact description of the project, but yeah. Anyway, so that's that. And how are people looking, or how is it looking for the labs because if you feel that it's way too much work, I'm willing to drop these presentations if you feel that you have problems with the workload. So please tell me if you feel that the workload is too high with to complete the labs. Especially yeah, so I guess most of you are already started working on lab 4, so yeah, just let me know if you feel that it's too much to handle, and you can send anonymous if you want to also. Just I don't know how if you have a lot of work in other courses as well. Yeah. Anyway, let's get started with chapter 6, consensus variance. So the main the main idea about this chapter is to look at some specialized variants of consensus, because oftentimes there is an application that uses or need to use some kind of consensus for coordination between processes, but it has some specific requirements. So it can be like I mentioned here, like only some specific values can be proposed. Remember when we looked at just pure consensus, we allowed any consensus value, but actually there might be some limitation by the application itself, and also there might be some requirements on the ordering of messages that it wasn't captured in the consensus where we allowed any order as long as the all replicas agreed on it. So this is kind of the main four, and many times in the literature you can find these names, what's it, in the parentheses, the total order broadcast, atomic commit, group membership, and so on. And when you see these names for protocols, you can now know that this is actually you can think of them, or they can be considered equivalent to consensus protocols. So in such a way that if you can have total order broadcast, you can also have consensus from this, and same with atomic commit and so on. So the first one we will see today is the total order broadcast. And if you are kind of like me, it's easy to get confused with all these names, because now we have seen FIFO, or first in, first out order broadcast, and we have seen CO broadcast, which I wanted actually to have this slide first, but yeah, we saw FIFO order broadcast, and we also saw causal order broadcast, and now we're looking at total order broadcast, and they're all broadcasting abstractions, but they have some slight differences. And so with the FIFO order, the abstraction enforced the ordering only on the sender. So when the sender the same order that the sender sent out the messages, the other processes could receive them in the same order. Then we extended this to causal order, which enforces global ordering on messages that causally depends on each other, meaning that the one happened before the other. But it didn't give us any guarantees on concurrent messages. So with causal order broadcast, we can run into this problem that's shown here, that one process does the add operation before the multiplication operation, gets the result 6, but another process does first the multiplication operation, then the addition, and gets a different result. So with total order broadcast, it's an abstraction that ensures that all processes deliver the same messages in the same global order. And one thing to keep in mind is that this is totally orthogonal to FIFO and causal order, meaning that total order of broadcast, it just ensures that there is one global order. It doesn't say anything about this order is right, or that necessarily a message was sent before another. It just ensures that there is some global order that every process can agree upon. So if we see from, I guess we can go to the next example here, that we have kind of two parts of the algorithm. One is the reliable broadcasting part, and another part is the consensus part. So we have like a reliable broadcast that we saw before, and once the processes gets or delivers the broadcasting message, they will run a consensus round to deliver up to the application layer. So here we see round, and keep in mind that this is not a Paxos round. This is a Paxos slot or Paxos instance, because we have in this total order broadcast, they say in round 1 we have consensus on the message M1, and in the round 2 we have another value, and so on. But remember in Paxos that you will have only one value or no value in every round, and once there is a decision, then you need to move to a new slot to have another value. So we can also find the name atomic broadcast instead of total order broadcast. Mean the same thing, and here is some other sequence flow that can be nice to look on. And here we have the three different kinds of broadcasting: reliable broadcast, causal broadcast, and total order broadcast. So if we see the total order broadcast, we can see that every replica has delivers the messages in the exactly the same order, whilst for the case of closed-cell order broadcast, there isn't an enforcement when there's concurrent senders. So we have both M1 and P1 and P3 sending or broadcasting messages, and this causes only P2 and P3 has the same order in this scenario, but the P1 has a different ordering. So this would not work for a replication type application. And the same issue with the reliable broadcast. The messages are just delivered whenever they are received. So you see, as soon as the application receives a message, it delivers it, and this causes in this scenario every process to have a different ordering. Whilst in the closed-cell ordering, at least we have an insurance or an enforcement for messages sent by the same process. So we have the insurance that M1 is always delivered before M2 because we have a closed-cell ordering between M1 and M2, but there's no closed-cell ordering between neither M1 and M3 or M2 and M3. Thus, these can be delivered in any order. But with the total order broadcast, it ensures that every message on every process is delivered in the same order. And you can see the main difference here is that in the two first cases, the P3 delivers M3 very early on, just right after it has broadcasted, whilst in the total order broadcast, it actually waits for having consensus on that value and doesn't deliver it until the very end. So what's the properties for this abstraction? So we have basically one new thing. We have the the properties 1, 2, 3, 4. They follows from the reliable broadcasting abstraction, and then we have another one, TOB5, property 5, which is the total order. Let M1 and M2 be any two messages, and suppose P and Q are any correct processes that deliver M1 and M2. If P delivers M1 before M2, then Q delivers M1 before M2. So this says that for all processes, all correct processes in your system, that they must deliver any messages in the same order. Please note the thing which isn't captured by this actually it is captured by this total order sequence flow here that if you examine carefully that P1 is the broadcast M1 before M2. So in the carousel ordering, then M1 should be delivered before M2 as it's here, but total order it doesn't have a requirement to respect carousel ordering. So depending on the implementation itself, it can respect it if you add this as another requirement, but for the usual description of the protocol, it doesn't have a requirement to respect carousel ordering. Is there any questions about that, or is it clear what's a total order and what's a carousel order? If not, just speak up or say it in the chat. And yes, and then similar to the reliable or regular reliable broadcast, we have also a uniform broadcast, and here also a uniform variant of the total order, which has the extended properties for faulty processes. So the ordering is it's valid even if the process is faulty. Here we have someone. Yeah, so M1, M2 be any two messages, and P and Q are two processes that deliver M1 and M2, whether correct or faulty. If P delivers M1 before M2, then Q delivers M1 before M2. So same thing as the regular total order, only with the added or the extended properties to also be valid for faulty processes. So the algorithm itself, it looks like this, and I guess you can be kind of surprised that it's so short and we have so many things going on, but yeah, the main thing is to realize that we are just using the abstractions that we looked upon earlier. And one thing to be especially aware of if you're trying to analyze this algorithm yourself is that there's some issues or not exactly issues, but some mistakes in the book, which is it's on the line. If I can, I know that it here. So there's a this. Yes, it's these two lines here, the delivered and unordered set. They should be inside the loop here. So we because here we are when we have a consensus, we have reached consensus. The site is triggered for some values in that round. We sort the messages, as you saw on this slide. It can be multiple values in one round. Here we have M3 and M4. Both of these values are decided upon in the same round, round 3, and they are sorted. So we have the decisions from the consensus instance. For that round, we sort the values in a deterministic way. They're very important. It must be deterministic, and then we should move this delivered line inside the loop and not have it have the delivered set be the both of the decided value, but it should be the S and M, so the two like the message and sender or the decided value. Yes. So I will not go more into that algorithm. Let's see if I have something extra. Yes. Yeah, and one thing also, which is kind of different from your Paxos implementation, is that here they use a waiting flag, so that they have only one, or they avoid multiple execution of or concurrent consensus executions. So there's a waiting flag whilst in your multi-Paxos lab you allow or you should allow multiple instances to run concurrently, at least in lab 6, I guess. Anyway, so then we can move on to Byzantine total order. Just want to check what's the time. Okay, 3 o'clock. So anyway, we have the Byzantine total order broadcast, which is yes, like a total order that we just saw, just in the fail arbitrary model. And remember, in the Byzantine broadcast, then every sender or every instance of Byzantine broadcast delivered only one message, and from a specified sender. So we knew beforehand who would be the sender in the Byzantine broadcast. So we are using that here. And we have the same properties as the Byzantine broadcast from chapter 3. Yeah, the integrity property must hold, and the integrity property, it ensures that there isn't any message forging. If some correct process delivers a message M with sender P and correct process P is correct, then M was previously broadcast by P. So we achieve this with use of MAX or digital signatures or some form of authentication. And yes, the other 1, 2, 4, 5 properties, they are same as the total order. All right. Then there is an example algorithm for this, and yeah, we see that we are using point-to-point authenticated perfect point-to-point links and Byzantine consensus. So this algorithm, it's in the fail noisy arbitrary model. So we don't have a useful failure detector, as you see, but we rely on an eventual failure detector obtained from the underlying consensus round. So we use the underlying consensus instance to have a leader abstraction. All right. So not sure if it's so interesting to go into details on this algorithm itself. So I think if there is no specific questions with respect to this, we can skip ahead to terminating reliable broadcast. Which is an extension from the reliable broadcast with the added properties for a deterministic resolution if the sender crashes while he's broadcasting. So in the case of uniform reliable broadcast, we can actually end up in two states because in the uniform reliable broadcast, we only remove the correct process from the we only remove the correct process from the crashed set, and we have no way to detect whether we should keep waiting for the broadcasted message or move on. So in the terminating reliable broadcast, there is a special value, this delta sign here, in such a way that all process delivers the message M if the sender S is correct. Otherwise, they deliver this delta value or a null value. So that's the thing with terminating reliable broadcast. And this is strictly stronger than uniform reliable broadcast. We have similar to regular reliable broadcast. So yeah, the RB, it means obviously the reliable broadcast, TRB, terminating reliable broadcast, and URB, uniform reliable broadcast. And yeah, like the reliable broadcast, we the correct process in terminating reliable broadcast, it agrees on the set of messages they deliver, and like the uniform reliable broadcast, they the TRB delivers every message delivered by any process, but unlike them, every correct process delivers a message even if the broadcaster crashes. So it doesn't, it terminates, it doesn't keep on waiting forever. So in the like we had this scenario from before, that the uniform reliable broadcast, it kept on waiting indefinitely, but with terminating reliable broadcast, it either delivers the message if it receives it, or it delivers a nil value. So I guess this is another nil value in this particular figure. So the module description for this has these properties, and again, yeah, the main idea here is that each process, it will deliver a message broadcasted by the sender, or a special nil value, which is delta, which yeah, they call it here. So yes, this is the pseudocode, and maybe we can first take a look on execution flow. So we have the case here that the process S, it broadcast a message M, and then it crashes, and it was only able to, or the message was only received by 2 processes before it crashed, and the last one didn't actually receive the message. So after this broadcasting phase, it enters a consensus phase where the protocol tries to reach a consensus of the values here, and since the M is the majority, then this is what will be delivered by all the processes. So So we are using a failure detector here, and it's kind of using the extending the underlying consensus instance with a broadcast and deliver, but we have the added properties with some specific value will be delivered if the sender crashes. So all right, any questions so far? Of course, it can be maybe too fast. Because I was thinking that maybe it doesn't make so much sense to go into the very details of the algorithm, since you will not have an exam in this. So instead, maybe go a bit faster than usual, and then we can try to use the extra time to for your project or something along those lines. To take a more in-depth look on specific relevant protocols. So yeah, the next type of consensus variants is the non-blocking, in quotes, atomic commit. And I'm sure if you took a database course, or you played around with databases on your own, you would quickly run into atomicity or the acid properties, and the main idea when people say atomic or atomicity is that either something happens completely or not at all. So a transaction is the unit which is is the unit which is is data processing unit in distributed information systems. And here a transaction, it means a specific part or part/portion of a program, typically delimited by end or begin and end statements. So oftentimes this is like that. You don't want like the typical example is when you have a transfer for a bank transfer type thing, that for example you want to let's say or transfer some funds from account A to B and then some funds from B to C, but you only want like you have the B as an intermediate actor, and you only want the funds from B to C to be transferred if there was funds from A to B transferred. and you can then have a atomic requirement for that specific or those specific transactions, so that it will never happen that only funds from B to C are transferred. It always needs to be accompanied by a transfer from A to B. And yeah, typically there's two semantics for atomicity. The concurrency atomicity. All transactions appear to execute one after another. So keep in mind the appear to. It's not necessarily that it really happens like that, but it appears so to the application layer, and thus we can have they are serializable, meaning that you can have a causal ordering or some ordering between them. And what I mentioned initially, the failure atomicity, that either the whole transaction completely executes. Oftentimes you will see the word commits, or not at all, it aborts. Yes, in the book they no longer call processes for a process, but they call a process also for a data manager. Mostly the same thing. But this looks a lot like a typical or consensus or binary consensus, meaning that either we decide or we don't decide, but we have some special properties. So the uniform agreement we will find from the consensus that no processes decide differently, and integrity, no process decides twice, and yeah, determination property we saw before also, that every correct process eventually decides some value. But we have two special properties here that that we have a abort message, or yeah, let's say a value, a special value for abort. Yeah, it says actually here also that it's only you can, in the non-blocking atomic commit, you're only allowed to propose two values. Either you propose commit or you propose abort. So so the commit, it's only allowed to decide commit if there is no process that proposed abort. So the if any process or data manager proposes abort, then it's kind of a veto type thing. So it's not like before we looked on consensus with had rules that was decided from the majority, if you remember. But here a process can propose an abort, and it will veto, so that no other process can commit. But a process can only decide on abort if another process proposes abort, or if the process itself crashes. So the algorithm looks like this. So, you'll find it in the book also, and it starts off by every process broadcasting its initial vote, meaning a commit or a abort value, and then we have on the delivery event we wait for messages, and if at any point there is an abort, we receive an abort, we immediately try to have we propose this value for the consensus, or if the value is not an abort, it's a commit. We aggregate them, and then we, as soon as we have received a commit from all the processes, so the voted, it's the set of all processes, then we propose the commit value. And yes, so yeah, when we detect a crash, we propose also an abort. All right. So that was what I had planned for today, actually. So yeah, I had plans to do group membership and use synchronous communication on Thursday, and just as a teaser, what is group membership? This it's a way to get a consistent view on the participants of the system. So if you remember from your implementation of the failure detector, it was possible that the different processes at any given time it suggests or suspected different processes, and after a while they kind of agreed, but at some point in time you could have this type of state where the P1 process suspects only P2, and the process P4 it suspects only P3. But whilst in a group membership, there's a consensus of this view, so that they both agree on the same processes. Anyway, yeah, I will continue from this chapter 6.7 on Thursday. But if there's any questions from the previous parts in the book, we can do it now. I didn't see any questions in the chat, and yeah, I didn't see any questions on Discord neither. So if everyone is content and feel that they have it under control, then we will end here and we will continue on Thursday. And by the way, I didn't have any message from any one of you regarding the class representative. So I know that I said that we would elect on last Thursday, but we didn't have a lecture, so yeah, we can I guess promote to Håkon to the representative. Yes, he can do the job, I hope. So yeah, if there's nothing else, no questions, then we will continue on Thursday. So bye bye everyone, and I'll try to end the call. So yeah, bye bye.